Hello, here's the Unit 2, Module 2 virtual office hours. These are all the problems that were worked out during office hours. And so if you want to compare your notes or look at problems worked out, I suggest viewing this video. Alright, so here's a photoelectron spectrum. And keep in mind the y-axis is the number of electrons, and the x-axis is a measure of how much energy is required to remove the electron, so that the most stable electrons are to the left and the least stable are to the right. The most stable here are in the inner shell, the n equals 1, that's the 1s2, there's 2 electrons there. Then there is a second shell, n equals 2, which has 8 electrons, and then a third shell, which also has 8 electrons. If we look at the electron configuration for this particular species, we would write this as 1s2, 2s2, 3s2, 3p6 for a total of 18 electrons. So when we look at the options, we're looking at what ion has 18 electrons. So for sulfur 2-, which has a Z of 16, so a Z of 16, that means it has 16 protons. It must have 18 electrons if it has a -2 charge. Remember, each electron carries a negative charge. Each proton a positive charge. O2-, its Z is 8. Total number of electrons must be 10 electrons to give it a -2 charge. Argon has Z of 18, so this does have 18 electrons, but it's not an ion. And neon 2- has a Z of 10, and to have a -2 charge, it must have 12 electrons. So the problem says ion, so the selection would be S2-. Argon is neutral, so that can't be chosen. So just keep in mind the total number of charges is the number of protons plus the number of electrons, and that will help you in these problems. In this problem, this is from a previous exam, we were asked to draw the PS spectrum of carbon and the PES spectrum of oxygen. So carbon has a total of 6 electrons. These 6 electrons are in the 1s2, 2s2, 2p2. Oxygen has a total of 8 electrons, so it'll be 1s2, 2s2, that gives us 4, and then we have to put 4 electrons into the p orbital. Okay, we see that there's more energy is required to remove electrons from smaller atoms. Okay, so this is giving some insight. Oxygen is the smaller atom. That means these electrons have lower potential energy, and therefore must have a higher ionization energy. Ionization energy increases going from right to left. So if we do carbon first, we show the 2 different shells, 2 electrons in the inner shell, 1s, 4 electrons in the outer shell, but in 2 different orbitals, 2 electrons in the s and 2 electrons in the p. There's the outer electrons and inner electrons. When we do the PES for oxygen, we have to shift everything to the left because the information in the problem says that oxygen has a higher ionization, meaning it requires more energy to remove the electrons, so they have to be shifted slightly to the left because the oxygen is smaller. All this information was given in the problem. Higher ionization for oxygen. Oops. So that's how we would draw the PES spectrum for oxygen. All right, so here we have a problem in which we want to identify which metal is this. What is the species of M? So one thing we're going to do is we're going to start populating to get some numbers. So we know that the small peaks, and especially the one farthest to the left, must be an inner core, 1s2. So the little peaks are 2s. The next peak is 6 because that's the 2p6. Maximum occupancy, and all of the inner orbitals need to be filled to their occupancy, so that's helping us. So we know that the p's have 6. This s has 2, that P must have 6. This, because these are all inner. This has 2. This is 10, 3d10, 4p6. And if that tall peak is 10, then that is 10. So then what we could do, so remember the maximum number of electrons, S's is 2, P's is 6, and D's are 10. And if these orbitals are to the left of any other peak, then they must be completely filled. Alright, so all of these must be filled. So that's how we knew what numbers to put. They're called inner core electrons. So let's add them up. The total number of electrons, we had 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 10. Total number of electrons is 46. So we have 46 electrons, and this gives the species a positive 2 charge. So that means we can calculate the number of protons here. So the number of protons plus the number of electrons, 46 electrons, has to be the total charge. Keep in mind that each electron takes on a -1 charge, so this is the number of protons minus 46 equals plus 2. So now we can calculate the number of protons by adding 46 to both sides. If we do that, we see the number of protons is 48. 48 protons are required to, when you add it to 46 electrons, you get a positive 2 charge. Look on the periodic table, and that element is cadmium. So the ion that's in these metals is going to be cadmium 2+. Okay. So here's another PES spectrum, another mysterious species that we have to determine what its identity is. So the first thing we do is identify, okay, it's a +2 charge, so we need to know how many total electrons are there. Well, if we look at the PES spectrum, we see there's a 1s2, 2s2, 2p6, 3s2, 3p6, and a 3d9. Now we need to identify, well, how many electrons are there? So we look at that, we see there's a total of 27 electrons. To determine the identity of the species, we have to know how many protons there are. So we say number of protons minus 27, because there's 27 electrons, have to be the total charge, which is +2. Solving for the number of protons, we see that the number of protons must be 29. That gives us the identity, copper. So copper 2+ is going to be the answer. This is the spectrum we would expect to see. So please keep in mind that when you're asked to identify a new species, the most surefire way to get the answer is to count the number of electrons, look at the total charge given, and determine the number of protons. Okay, so here we have selenium, tends to be -2. Let's build the photoelectron spectra and explain why the -2 state is more likely than the -3, and what is the common bonding pattern for selenium. Alright, so if we look up selenium, selenium has 34 electrons. So neutral selenium, if we were just going to write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, that gets us up to the orbital, the outer orbital, which is going to be 4p4. Alright, so that's neutral selenium. And now the question is, why is it in the -2? So when we put 2 additional electrons in selenium to give it a -2 charge, we see what happens, that it closes the outer shell. So the full outer shell is why selenium takes on a -2. If it was -3, it would have to open up a new shell, which would be very high in potential energy, and that is why there's no -3 state, or much less likely in the -3 state. It's also why selenium's bonding pattern is 2, because selenium must, or its bonding capacity is 2, because selenium must form 2 bonds to share the additional electrons from the bond to obtain the full shell. So selenium needs to make 2 bonds to fill its outer shell. All right, so what would we expect arsenic to do? So selenium was -2. What charge would arsenic have if the lowest state is the lowest energy state of the ion is going to be the full outer shell? So we look up what arsenic is, and arsenic has 33 protons and 33 electrons. We place them in the orbitals, starting with the lowest potential energy first. So 2 in the 1s2, 2 in the 2s2, 2p6, 3s2, 3p6. So just keep in mind we're just adding these up. So there's 2 in this first shell. Then we add all of them together. The first and second shell, we get 10. Adding up the third shell, we get a total of 18. So 4s2, 3d10, that gets us to 30. And now we have to add 3 electrons. Electrons 31 through 33 go into the 4p3 to give us a total of 33 electrons. But the full shell, the full outer shell of 4p6, to do that we need a total of 36 electrons. So if we had 36 electrons for arsenic, we would have the full outer shell. So we only have 33 protons. If we did have 36 electrons, the total charge would be -3. So arsenic, the most stable form of the ion of arsenic, negative ion, would be -3. If we had to sketch the PES spectrum, so the most important numbers here are 2, 6, and 10. So we would put the first one, 1s2, 2s2, 2p6, 3s2, 3p6, 4. Okay, so I'll just write these in so we see what these are. And then 4s2, 3d10, and then 4p6, right? So that would be the full outer shell, 4p6 for arsenic 3-. All right, so make sure that when you're drawing the PES spectra or if you have to draw them, that you show how the separate shells, you show that the lowest potential energy are to the left, and that you show that the individual peaks within a shell are separated, are really close together compared to the different shells, which should be well separated. Okay. Alright, so we did this problem already. So this is a problem of looking at, well, I did it. So just take a look here. So again, if you're given a PES spectrum, you count up the total number of electrons, which we did, 46. You add up all the electrons, it's 46 electrons. 46 electrons plus the number of protons must be the total charge. So that means that the number of protons must be 48. So that would be cadmium, and that cadmium would be with a 48 protons to give you a +2 charge. All right, so we've had some questions on the Top Hat homework. So let's take a look at ranking neutral atoms. So the trend here down a column is at the bottom, right? So the size increases as you add outer shells, and that is the primary consideration, is outer shells. So we would have a primary consideration of the outer shells, meaning bromine is going to be the biggest, chlorine, then fluorine the smallest. If we had to rank that in size, it would look like this. Now the question is, where does carbon go? Carbon is in the same row as fluorine. It's got to be bigger, right? So carbon is going to be bigger because the trend here is that it increases, the size increases as you go from right to left because there are fewer protons holding in the electrons, and so they get a little bit bigger. But this is secondary compared to the outer shell trend. So if that's the case, then carbon is bigger than fluorine, but we would predict it to be smaller than the next outer shell, which would be chlorine. So we would put this order as carbon is a little bit bigger than fluorine, but still smaller than chlorine and then bromine. So we would pick that answer. Next question we've had several inquiries about is this one, which has to do with ions. So let's keep in mind that electrons repel each other. So that's what creates the size of the atom, our electron-electron repulsions, and their competition with the electron-proton attraction. So here we have, so the more electrons we have, the bigger the size. So that means that if we were looking at a neutral atom versus a -1 charge, which has one additional electron, or a -2 charge, then -2, which has the additional electrons, would be the biggest because of these repulsions, and the neutral species would be the smallest. We could extend this into positive charges, which means there's actually more protons than electrons. And so these are going to be the smallest. They're definitely even smaller than the neutral species because there's more protons holding in the electrons even closer. They're far more stable, the electrons. They're getting closer to each other with this increased protons. And so what we see here, if we had to rank the size, is +2, +1, 0, -1, and -2. So +2 is definitely the smallest, meaning there's 2 additional protons holding in the electrons, versus the -2, which has 2 less protons than the number of electrons. This increased electron-electron repulsion and the lack of protons lead to the largest size. So positive ions are always going to be the smaller, largest would be negative ions. And so if we look at this particular problem where they all have the same number of electrons, we would pick the smallest to be calcium 2+, and the largest to be sulfur 2- based on this analysis. Okay, and so the very last part of the analysis we talked about was with bonding. So let's say we have carbon bonding, and here it has 6 electrons, and here carbon has 6 electrons. What we're going to do is we're going to take one of the 6 electrons here, and we're going to make a bond. We're going to take 1 electron here and one electron here. And what we're saying is, in the atomic states, these have high potential energy and high kinetic energy. High potential energy and high kinetic energy. You say, why is that? Because there's electron-electron repulsions of 6, right? There's 6 electrons, and there's a small atomic orbit. So this is true for both. There's 6 electron-electron repulsions here in small atomic orbit. So then when a bond is made, so this is energy going up this way, potential energy. Now when a bond is made, carbon we now have a molecular orbit that is bigger than atomic orbit. So the kinetic energy goes down in the bond. And then 5 electrons have less electron-electron repulsion. So the potential energy goes down. So in the bond, what we see is the bonding, what the bond does to the bonding electron that goes in here, it's going to go through a bigger orbit, so lowering the kinetic energy, and it has now less the 5 remaining electrons on the atom have lower potential energy, and so this is going to be more stable Whoops, more stable. And this is less stable. So energy is required to go from a bonding scenario. So here's A up to B. So if we're going to break a bond, right? If we're going to break a bond going from A to B, or the CC going to C plus C, if we're going to do that, the total energy must increase. That's because we're going from a low kinetic energy, low potential energy, up to high potential energy and high kinetic energy. So energy goes up. If we're going from B to A, meaning we're making a bond, going C plus C atom, making C bond C, well then total energy goes down. That releases energy. So making a bond releases energy, breaking a bond requires energy. So we went through this in office hours in great detail in this way, using both potential energy and kinetic energy arguments. Okay, so this is all the topics that were covered in Unit 2, Module 2 during office hours. Several other topics were covered in Unit 2, Module 1 and Unit 1, Module 4, but those have been covered already in the virtual office hours already posted. All right, good luck.